In this brief lecture, we're going to look at the conservation of charge and a special equation known as the equation of continuity, which expresses the conservation of charge. We've seen that in electrostatics, we have equations relating electric field or electric flux density to charges or charge densities. And in magnetostatics, we see equations relating the magnetic field or magnetic flux density to currents. And you may be wondering if there's a relationship between charge and current. And indeed there is, because charges cannot be created or destroyed. And we can actually express this in an equation known as the equation of continuity. Later this lecture, we will talk about what the circuit equivalent of this law is. So as we progress through, think carefully about a circuit law that also expresses the same thing. So to begin our discussion, I want you to consider a closed surface S. And in this case, it could be a three-dimensional volume. So I'll try to express that here by making this look more three-dimensional. And this closed surface S is also fixed. We're not going to allow S to change with time. It's just a fixed area, a fixed volume V internally, which we are considering. And inside this volume V, there is some charge. And the total amount of charge stored in this volume is Q sub I. We'll use I to indicate that it is internal to the volume V. Let us also imagine that there is some current leaving this volume V. And we'll write this as a current density, J, which is a conduction current density. So if we know the area over which J is measured, we can work out how many amperes of current are leaving. So this is the conduction current density passing through S, the closed surface bounding the volume V. So now let's write an equation that expresses the total current leaving S. Okay, so let's write that as the total current leaving this closed surface S. And we'll call this I. Now we know I is related to J through a flux integral. So if I integrate over S and I integrate J dot ds, that should be the total current passing through S. But since S is a closed surface in this case, we should put a closed loop here to indicate that S is closed. And this is a total outward flow of positive charge, right? Because when we think of a current I always points in the direction that positive charge is moving. And since we're integrating J dot ds, this is the flux leaving S. Okay, so this is an important point about what I denotes here. Now let's return to the charge internal to the volume. So that is Q sub I. So if this charge, Q sub I, is the total charge inside S, then if there's indeed a positive J or a positive outward flow of positive charge, then the amount of charge inside S, that is Q sub I, must be decreasing with time if I is a positive quantity. So let's write that down. Q sub I is decreasing with time. If this current I that we have just defined is positive or greater than 0. So we cannot create or destroy charges. So if charges are disappearing from the surface S, i.e. Q sub I is decreasing, it's because those charges have left S. They haven't just winked out of existence. They've moved outside of S because they cannot be destroyed. So the way that we can write this mathematically is that the current, which is the closed surface integral of j dot ds, as we wrote above, is the time rate decrease of the charge within S. So the way I write a time rate change of q, or q sub I, is by taking its derivative. And because it is decreasing, we need to put a minus sign. This equation that we've just written here, this integral equation, is the equation of continuity. And it is an integral equation for obvious reasons. So it is about the continuity of charge and current. We cannot create or destroy charges, and so anytime there's a change in the charge level is because there is a current present, and the amount of current is related to the amount of charge present through a negative time derivative. We can actually manipulate this expression in order to determine the point or differential form of this equation. We can do that by applying the divergence theorem. So we haven't seen the divergence theorem since visiting Gauss's law. You may recall that it allows us to relate a closed surface integral, which we see here, to a volume integral. So this closed surface integral becomes a volume integral, which is a triple integral, of the divergence of j. Meanwhile, the right-hand side is the time derivative, negative, of the charge enclosed in S. And we can find the total charge enclosed within S, or over the volume V associated with that surface S, by integrating the volumetric charge density dV. So this portion over here, this is Q sub I. This is just a fundamental relation between charge density and charge, which we have seen a long time ago when we talked about Gauss's law. So now we have two volume integrals. So we can basically equate the integrands. Before we do that, we should move the time derivative that we see outside on the right-hand side inside. Now, since we're changing the order of operations, we need to be mindful of something, because right now, if we integrate rho sub v over space, we're left with rho v purely being a function of time, and so we're allowed to take an ordinary derivative that we see here. But if we interchange those operations and we take the time derivative of rho sub v first, we have to bear in mind that rho sub v itself may have some spatial dependence. So when we move that time derivative inside, it is going to become a partial derivative, which we indicate like this. And otherwise, the integrand remains the same. So now we indeed have two volume integrals that we can equate. We can equate the integrands. So the integrand on the left-hand side is divergence of j, and the right-hand side is the negative time derivative of rho sub v with respect to time, partial derivative. So this is the equation of continuity in differential form, because clearly we have a differential equation on the right, and divergence is a differential equation in space on the left. So this is the point form or differential form of the equation of continuity. Now, at the beginning of the lecture, we asked the question about what is the circuit equivalent of this law. So basically, we cannot create or destroy charges. So current, the change in charge must be related to a related current. Currents are associated with the time rate increase or decrease of charge. So hopefully you've thought about this question a little bit. This is basically an expression of KCL, which is Kirchhoff's current law. Kirchhoff's current law is saying the same thing, because we know that we cannot create or destroy charges. So if we were to analyze KCL at, let's say, a junction of two wires, let's draw a wire here, and let's say there's another wire connected to it. So we have a three-way junction of these wires. Well, now let's draw a closed surface S, just like the one that we drew up above. It can be any shape that we want. It's a closed surface. And these three conductors pierce through S at certain positions. So maybe this conductor pops out of S at this point, maybe this conductor pops out here, and this conductor pops out here. So we have three discrete points where currents leave S. And maybe we can assign currents like so. So I1 enters through here, I2 leaves through here, and I3 leaves through here, just all arbitrarily. So across each of these surfaces, we must have some corresponding current density. We might call this J1 passing through this surface, J2 passing through that one, and J3 passing through the one on the bottom. If we were to apply the equation of continuity here, it says that the closed surface integral of J dot ds must be equal to the time rate change of the charge stored within S. Well, within S, I don't have any charge storage at all, right? This is just a junction of two wires. I don't have any charge storage mechanism in this junction. I can't store charges in a metal wire junction like this. So the right-hand side here is 0. And we know that if I integrate J dot ds, the only place where the integrand J dot ds is 0, or non-zero, sorry, is over this surface, this one, and this one. So if I integrate over surface 1, I'm going to get I1. If I integrate over surface 2, I will get I2. And if I integrate over surface 3, I will get I3, right? Because I'm integrating J1, J2, and J3 over the corresponding surfaces. But notice that we have signs here as well. So I1 is entering S, so technically I1 is negative from a flux perspective, whereas I2 and I3 are leaving S, so they are technically positive from a flux perspective, and their sum must be 0. So we recognize this as a KCL type of equation, and KCL, indeed the way we write KCL normally when we're analyzing circuits, is that the net outflow of current must be equal to 0. We could also write it as a net inflow of current must be 0, but regardless of the reference direction that we choose, the way that we normally write KCL is that if we sum up all of the currents at a node in the circuit, and let's say there are K currents present, they must sum up to 0. So this is a circuit equivalent of the equation of continuity, bearing in mind, of course, that in circuits we don't have a mechanism for storing the Q sub I that you see in the equation of continuity. So this equation, particularly the one in point form that we see here, is going to be useful when we update Maxwell's equations to reflect time-varying fields. And we'll do that in a separate lecture.